Here it is.
Hello. In this recording, what I'm going to do is review some of the concepts between an open and closed system and add to the closed system some discussions that we have not done before on closed systems and work done on them and by expansion of the gas. Remember that the energy balance for closed systems is, as we have demonstrated, in a closed system, the change in energy is an internal change of energy. So we have heat, which is this Q. Remember that this Q will be different if we have, whenever you're taking the hydraulic engineering course, for civil engineers, that Q is more like volumetric flow rate. For us in this class in thermofluids, Q is heat and W is work. So the change in energy would be the notation Q minus W, but really would be the summation of all the Q in plus the summation of all the work in plus the summation of all the work in plus the summation of all the work out. So we can establish that difference by saying that the work is in or out, or work or heat going in and out of the system, or otherwise stating it in the standard notation where if Q is going in the system, then we have positive. If Q is going out of the system, then it's negative. And in the case of work, if work goes in the system, then it's negative, and work out of the system would be positive. So, the notations, remember that we use our lowercase, uppercase notation to determine if it's per unit mass or not. In the case of capital letters, we have energy. Remember, Q and E are also forms of energy, so they have the same units. And if it's lowercase, it means per mass. The differential forms, we use the squiggly, which is the delta, lowercase delta, for each one of the systems. In the case of an open system, what we see is quite different, but we still have heat transfer and work transfer. In the case of an open system, the difference is that we have input of mass or output of mass going through the boundary of the system. That's what makes it different. But we still have, or can have, energy. This would be this. So what we have is outputs of mass and inputs of mass. This too we could have in the open system, but we would have here then not necessarily heat and work in that way, but we will have mass going in and out. Then we talked about total energy and total mechanical energy, and these are concepts we'll talk about a little later, but the important thing is that the total energy equals the internal energy plus the kinetic energy plus the potential energy. So this U is internal, K, remember, is for kinetic, and P is for potential. So this is the total energy, and the total energy should remain the same for the law of conservation of mass. However, whenever we talk about fluids, especially incompressible fluids, that internal energy is not usable energy. So we do not use the internal energy to calculate the mechanical energy change of a fluid during incompressible flow. So what we have is a change in mechanical energy. Now remember, we have fluid going in and out of the system, so this is for open systems, okay, where you have flow going in and out at a certain velocity, and this is applicable for fluids. In this case, we will see how that would be different from steam that would be compressible. In this case, it's incompressible fluids, and mostly we use this for water. This is a civil engineering class, so we focus on water for that case. So, as usual, we have the mechanical energy, and its lowercase, in that case, is per mass. In the case of energy, remember we have total energy, and then the dot means it's energy per time, which is power. I encourage you to look at other videos that I've uploaded that describe the dimensional analysis of this equation in the metric and also in the U.S. customary units. Remember, the energy belongs for closed systems. Again, we are repeating the same thing, but whenever we talk about change in energy, energy in minus energy out, in the case of the closed system, the energy in and out only goes in and out in the form of heat or work. And you will have copies of this slide, so I encourage you to look at them and look at the units in each one of these, because we have lowercase and uppercase, and we can have then the total heat would be the heat per time multiplied by the time. Whenever we talk about the work, we talk about the work per time multiplied by time. So in case that you have an equation or a differential equation, this would be the equation you would use. Of course, remember that we're going to see here very simple systems, because this is a basic thermodynamics course, but it's important that you understand what those variables mean. Energy transfer by heat, we talked about this already, and in the case of heat, one of the things we studied was the specific heat capacity of the systems. So whenever we talk about heat, we will talk about heat transfer, and in the case of work, remember that it's different from heat. For heat, the driving force is the temperature difference. So if there is work transfer from the system to the surroundings, so from the surroundings to the system, but there's no driving force or no temperature difference, then all you have is work. And in the case of work, it can take different forms. The basic definition of work is the force acting for distance, so work is a form of energy, of course. And these are the two most common ones that we'll see here, mechanical and electrical. And the mechanical could be a shaft or a spring or a rising piston. So we will, what I want to do is talk a little bit about the rising piston, because we did not talk about that. We have talked mostly about shafts because we'll look at energy produced, and pumps and turbines have shafts. And then electrical work, which you would have to have an electrical wire crossing the system. So if you don't have an electrical wire, then you don't have electrical work. Other forms of work, you can have a solid bar, liquid film with wire. Non-mechanical could be mathematical or polarization. But as I mentioned, again, we'll look at electrical, and in case of mechanical, we're going to look at this and this. And in your book, you can see the transfer of work in and out of the system by springs. the moving boundary work then is P times V. Let's do a dimensional analysis real quick. P times the change in volume, and if it's a big change, we use delta instead of the differential. But the units for pressure are newtons over square meters, and the units of volume are cubic meter if we're talking about the metric system. So this will cancel, and I will have Newton meters, and Newton meters is joules. So we have here that the multiplication of pressure times volume, or change of volume, is joules. So there's work. Now let's say that you're applying pressure and there's no change in volume, then you're not doing work. Remember, it's like pushing a car that's not moving. You are not doing work unless that car moves. And you learn this from statics and also from dynamics. So this is very important. If there's no change in volume, there's no boundary work. There's no expansion or compression. And this case would be like a closed system where you have a gas and a piston, which you've seen in many situations. So the work would be a change in volume, and you either increase the volume or decrease the volume. So let's take a look at this. I want to just show you what the difference would be between work being done by the system or on the system, depending on the change in volume. If you are increasing the volume of a system, the piston is moving up. If the piston is moving up, that means that the system is doing work on the surroundings. However, if you do the opposite and then push on that piston, what you do is decrease the volume. And by decreasing the volume, you're putting force on the system, it's decreasing, so you're doing work on the system. So the definition of work has to be applied here on the standard notation, which would be if you do work on the system or by the system. Remember, the change in energy is Q minus W. So if work is being done on the system, that means that this is negative. And then what you will see is that the volume will decrease. If work is being done by the system, the work notation would be positive, and then the volume will increase. So if we are talking about differential equations, remember that we're saying, okay, work is P times delta V. But if you have very small changes in volume over time, and you want to calculate the exact amount of work, then you have to go with the differential equation. But definitely, you know, what this means is that you have an equation or a line of pressure and volume. So the change in volume is a dV instead of a delta V. So the area under that curve will be the total work. So depending on the path would be the work. So if I go from one point to from point 1 to point 2, following A, I have work. Following B, I have a different amount of work because the area under the curve will change. So this would have a larger area if I go under A than if I go under C. So depending on the path is the work that you do on the system or by the system. So this is what I mentioned originally. So work is positive if it's expanded. Remember, change in energy, or I already have it here, is Q minus W. So if I have to do work on the system, I'm adding energy to the system, so work has to be negative. And if work is negative and I'm doing work on the system, would be a reduction in volume, so it's compression. And work would be positive if I do work, or the system does work on the surroundings, because then the internal energy of the system is reduced. And so what happens is that you have expansion of the gas. So as I explained to you, we're going to be flipping the class. So this is just the classroom portion, and that example we will do in class, example 5.1 on page 148, as well as example 5.2 in page 149, so be prepared to work on those. So this concludes the review of closed systems and open systems. I hope that this has been helpful. Send me an email if you have any questions. Thanks.